Why flare gas recovery is not always the right choice in many refinery and petrochemical flare system discussions. Flare gas recovery is often seen as a default improvement, reducing emissions, recovering energy, and improving efficiency. At first glance, it sounds like an obvious upgrade, but in real engineering projects, the decision is rarely that simple. Flare gas recovery is not designed for all scenarios. A flare gas recovery unit (FGRU) is typically designed to handle continuous or routine low-flow flare gas, such as tank breathing losses, continuous purging, small processing vents, minor operational fluctuations. In these cases, recovering gas back into the fuel gas system makes both economic and environmental sense. However, flared systems are not only about routine operations. The real challenge, emergency and peak relief case flare systems, are fundamentally designed to handle unpredictable and high-intensity scenarios, such as emergency depressurization (ESD), PSV simultaneous relief fire case relief loads, major compressor trip event startup, and shutdown transients. These events can generate extremely high flow rates in a very short time. And this is where the key limitation appears. Flare gas recovery systems are not designed to handle peak relief loads. They are sized for stability, not for worst-case emergency scenarios. Why not send everything through recovery? In theory, recovering more gas sounds better. In practice, it introduces several constraints. Compressor capacity limits response time during sudden surges, system stability. Under transient loads, risk of bottleneck during emergency relief. Complexity of control logic during upset conditions. If a flare gas recovery compressor becomes part of the relief path, it can unintentionally become a process constraint during emergency scenarios, which is exactly what flaring systems are designed to avoid. LNG terminals versus refineries. Different philosophies. In refinery systems, flare gas recovery is more common because there is often a significant amount of continuous, low-pressure vent gas that can be economically recovered. In LNG receiving terminals, the situation is different. Most LNG systems prioritize boil-off gas bog management via compressor fuel gas utilization within the plant or condensation systems where applicable. In many cases, the flare system remains the ultimate safety layer, only activated during abnormal or emergency conditions. This difference in operating philosophy leads to very different systems configurations. Engineering trade-off, efficiency versus safety margin. At the core, flare gas recovery design is not just a technical decision. It is a trade-off between energy efficiency, environment and performance, capital cost, operational complexity, emergency response robustness, and in safety-critical systems. One principle always dominates. The system must perform reliably under world-case conditions, not ideal conditions. Key takeaway: flare gas recovery is not a better flare system. It is simply a different design philosophy applied under specific operating conditions. A well-designed flare system does not aim to recover as much gas as possible. It aims to ensure that, when everything goes wrong, the system still works. I would be interested to hear from others. In your experience, what determines whether flare gas recovery is implemented in a project? Economics, regulations, or process philosophy?